So my name is Ben Seri. I'm the VP of Research at Armis. And today with me, I have Dor Zusman. He's a researcher on my team. Armis is an agentless IoT security company, which is focused on security in IoT devices and unmanaged devices in general, specifically in enterprise organizations. Part of the goal of our company is to better understand the threat landscape that IoT devices and wireless protocols in general pose on the security of an enterprise network. So part of this cause led us to this research, and it started by understanding that there is a recent trend in which enterprise-grade access points actually embed in them an additional radio chip, a BLE, a Bluetooth Low Energy chip. And this additional chip is there to have new features for access points, but it also naturally introduces a new threat landscape and opens the possibility of a network breach coming from a BLE connection. And in fact, in the process of this research, we found two zero-day vulnerabilities affecting TI BLE chips that are used by Aruba, Meraki, and Cisco access points. And so, what is our agenda for today? It's quite packed, so I hope we managed to get to everything. But initially, I'm going to talk about BLE in general. Where is it used? Why is it used? How is it being adopted in different verticals in the environment? And then specifically on access points. Why is it used in the access points? What are the features that are embedded in access points for carrying out BLE functionalities? Then I'm going to talk about over-the-air firmware upgrades for BLE chips. So what are the mechanisms for allowing OTA firmware upgrades in BLE chips? Are they secure? When are they secure? And so forth. And then we're going to discuss the two vulnerabilities that I mentioned. The first is the vulnerability that affects Aruba access points, their BLE firmware in the BLE chip that's used in their access points. And then I'm going to talk about the second vulnerability, which is vulnerability in TI's Texas Instruments BLE stack that is used in many of their BLE chips. And this is an RC vulnerability. I think maybe as far as I know, first vulnerability found in a BLE controller or Bluetooth controller level, right? So really close to the hardware level. And Dor is going to talk extensively about how we exploited this vulnerability on a Cisco access point and the general impact of this on networks and the security of BLE as well. So to begin, just a bit about Bluetooth Low Energy. Why is it used? What is the benefits of having Bluetooth Low Energy in different environments, different verticals? So Bluetooth Low Energy is kind of the cool new kid around the block. When you look at Bluetooth protocol in general, it's been around a few years, but it's really got adopted very fast by many industries. There are good causes for this. It is the newer version of Bluetooth, so it doesn't have many of the old generation code that was involved in Bluetooth, so it's much cleaner. And it's also low energy, right? So there was a lot of applications that can benefit from it being low energy. And it is being used in many verticals, like I mentioned. It's used in healthcare devices, medical devices, in healthcare systems in general, in manufacturing, warehouses and facilities, in retail, and in general IoT devices that you can find throughout offices. But why really is it used in access points? What is the use case there? So access points has the advantage of already being deployed throughout many organizations, right? They are the backbone to serving Wi-Fi to the entire organization. So they're already, the infrastructure is already there. So any application that uses BLE can benefit from the fact that an access point can be part of that application since it's already deployed in the organization. And in fact, there are many different applications that take advantage of this ability. You have indoor navigation systems, for example. You want to do navigations inside a closed building, and so the access points will send out beacons, which can help implement indoor navigation systems. You can also see them in medical asset tracking applications or other asset tracking applications where you want to track devices, their location, and so you put a beacon on the devices you want to track, and the access points will track these beacons. Retails also use BLE for customer tracking, or what we also look at as spying on their customers in some sense. This allows them to engage with customers, right, and to know if some specific person entered the shopping mall or something, and now we can show him a specific advertisement or something. And then you have the last use case that's getting traction also in recent years is the use of smart sensors, mainly in manufacturing, but others have it as well. The sensors will send out the reads over BLE beacons, and access points can serve as gateways to those beacons, connecting them to the cloud or the internet in general. But really, when we looked at the vulnerabilities found in these devices, in these chips, and their effect on access points and on networks through those vulnerabilities, our impact was similar to the internet's impact once we released our research. Why really do you need BLE in access points? And like one person wrote in Slashdot, obviously it is there to increase the attack surface. So, as I mentioned, there are two vulnerabilities we found and we're going to discuss today. BLE stack has different layers and different functions in the layers. In TI's chips, we're going to talk about most of these layers are embedded inside one chip. It's a system on chip, so it embedded all of these layers inside the chip. But it can also be split between a couple of different processors. It's much simpler than the classic Bluetooth. It's not so many parts, but essentially you have in the controller layer, you have a physical layer, you have the link layer that does most of the basic functionalities, low-layer functionalities for the protocol. And in that link layer, we also found one vulnerability, as I mentioned, that affects BLE stacks in TI chips. And these chips are already also used by Cisco and Meraki access points, so they affect these. But they can also affect other devices, right? Because it's a BLE stack vulnerability in these chips. Any device that uses these chips in the vulnerable state will be affected by this vulnerability. So it has a potential to affect many devices. When you continue up the stack, you have all these parts that are in the host layer, and they are their function is more high level. They creating connections, listening for connections. You have this specific part is called GAT, which is the most simple way to transfer data over BLE. It's like a REST API, if you may, like for BLE. So it allows you really a simpler way to transfer data. And on top of that, you have a specific application, and that will obviously change between one device and another, what is its use case of BLE. And in this layer, we found the vulnerability that affects Aruba, which I'm going to talk about now. So when you look at over-the-air solutions for firmware upgrades in BLE chips, so these chips are standalone devices, right? You don't have any other communication channel other than BLE. They are not connected to the internet. They're standalone. You can find them in IoT devices or even in access points where they're alongside another processor. And so they need to find a way to do firmware upgrades over there, over BLE. And so we wanted to see what are the challenges in these solutions. There are two major vendors that do BLE chips as standalone system on chips. Texas Instruments and Nordic Semiconductors. There are others, but just for the use of for this, let's consider these two. And they have each a separate framework for doing OTA upgrades. Texas Instruments has OED, over-the-air download, and Nordic has DFU, device firmware upgrade. So the challenges in securing these solutions, these frameworks, are obvious, right? You need to find a way to transfer the firmware over BLE in a secure manner so it can't be captured. BLE has encryption, but in order to use that encryption, the best way to do so is to create a bond, a BLE bond, which is the equivalent of Bluetooth pairing. And so that's another challenge. You want these connections to be over a bonded BLE connection. And then you want to use authentication. That's also connected to the fact you have you've done a BLE bond prior. So is the connection authenticated? Can you validate who is doing the firmware upgrade? And lastly, but most importantly, you want to validate the integrity of the firmware that is being uploaded, either with a digital signature or in other means you want to validate that the firmware is really trustworthy. In practice, these frameworks exist for a few years, but not so many. The recent versions are more secure, but the ones that are used today in market are not that secure, or not secure at all. The firmware are passed unencrypted over the air. GATT connections is not authenticated. Again, this is by the default configuration. Each application can change this, but by default, it's not authenticated, and the firmware is not validated. Or if it is validated, it uses a weak cryptographic signature that can be abused. So when we looked at an Aruba access point, we wanted to understand what is the attack surface here. And so the first thing that we did is we tried to connect to GATT when the Aruba is in beaconing mode. So an access point has different modes when it's using the BLE functionalities, but the most basic one is using a beaconing mode. It just sends out a specific unique identifier over advertising packets. But to our surprise, even in that mode, the GATT was still open and we can connect to it and see the services that this device exposes. More interesting was the specific unique identifier, which is TI's OED service. So it seems there is just maybe the ability to upload firmware to this BLE chip over OED. A bit about OED in general, just to understand the mechanics of it. It's pretty simple. You have a user, there is a device you want to upload its firmware to it. The first thing is initiating a GATT connection, and then you can send an image identify message, a simple message with a firmware header in it. And if that firmware is in the correct version or something pretty simple, the device will acknowledge it by sending an image block request, which will then follow an image block message sent from the user to the device containing a chunk of the firmware. And this will continue, this process for sending chunks of the firmware will be in a loop until all chunks have been sent, at which point the device will reboot into the new firmware. So very straightforward. So naturally we tried just uploading our firmware over OED to the Aruba access point, and it didn't really work. We initiated a GATT connection, we sent an image identify, but no response was received. So something was customized by Aruba's implementation, and we wanted to find out what. So the logical next step, let's open this up, let's hook up the debugger and dump the firmware. And in fact, when looking at this function that does the OED functionalities in the firmware, we noticed there is an additional call to memcompare here. So maybe Aruba added, like I mentioned, something custom that validates an OED in some sense. When you look at TI's OED function, this function receives any GATT write request and then dispatches them to specific functions. So it's very simple. You compare the unique identifier that's being written right now to the image identifies UID, and if it is so, you can call the function that handles that message. And if you find it to be equal to another value for the image block message, you can call that function that handles that message. So it's very straightforward. In Aruba's implementation, like I said, we found that there is an additional code here. And zooming in on the memcompares that I talked about before, there is just 2 more memcompares or 3 more memcompares here that validate another unique identifier. And if you write a specific unique identifier of the OED unlock UID, with a specific value, with the OED cookie, then that unlocks a specific global state, is already unlocked. And if you do this with another value, that unlocks another state. And this is some pseudocode of the function that we reverse engineered before. So obviously, Aruba added a hard-coded password to their implementation. It is not meow 1, 2, 3, 4, but it's not a good solution either way. And so really what this is the ability to upload firmware over BLE on an unauthenticated connection using this hard-coded password, and then you can have your own malicious code on this BLE chip. So what can an attacker do by gaining access to a BLE chip inside an access point, right? Initially is still confined to only being affecting this specific chip. How can he continue his attack? What is the next step for him? So Aruba access point design is such that the BLE chip has access to 2 UART interfaces, serial UART interfaces. One of them is used for configuration of the BLE chip from the main CPU and from BLE packets being sent back from the BLE chip to the main CPU. So this interface is one avenue for an attacker to look for additional vulnerabilities to try and target the main CPU of an access point. But another one exists here that is actually much simpler. Aruba access points can be configured to allow a user to connect to a console, to a terminal console, over a BLE connection. So this is the same console you get if you connect a serial cable to a network device, but this is offered over a BLE connection. And this could be useful in some scenarios where the access point needs to be configured, for network configurations, but it's not physically accessible. It's way up in the ceiling or something. So this feature is implemented by the fact that the UART interface between the console and the main CPU is shared with the BLE chip. So the BLE chip may be able to use this interface by an attacker and get access to that shell interface. And this shell interface exposes a few commands. You can configure the network configurations of an access point. You can even send packets within the network. It can be password protected, but it actually can also be not password protected. It's not a must, and that password can also potentially be brute forced. So it's not a hard security solution. So how would an attack with BLEEDINGBIT look like? How would it be carried out? First, like I mentioned, you can upload the firmware to a BLE chip using the hard-coded passwords. Then the attacker can use a firmware that gives him access to this console connection. Although this connection is configurable by the main CPU, the BLE chip is the one that carries out whether it's on or off. So once you're on that chip, you can make it access that UART interface regardless. Looking at an entire network here, or zooming out a bit, an access point will generally have access to multiple segments, right? It will serve both a corporate network and a guest network, or maybe other segments. So gaining access to the main CPU of an access point can potentially lead an attacker to access all of these segments. If the network is connected to the internet, like many are, an attacker can also take advantage of this and create an outbound connection to a CNC server. And at that point, he no longer needs to be in the vicinity of the device that he's attacking. He doesn't need to use BLE. He can create a backdoor over that CNC connection, and then the attack can continue over the internet. Okay, so we wanted to see how an attack like this will work, and because we are also engineers and we like the idea of it, we decided to take the attack airborne, as you'd see in a minute. Yeah, so our office is in Tel Aviv, in a high floor. So we wanted to see if we can come from the air, literally, and attack an Aruba access point sitting in our office. We installed an Ubuntu on an old Nexus 5. We attached it to a drone. I'm the hacker for this demonstration. And the smartphone is connected with a cellular connection to a CNC server, which the laptop is also connected to. So the laptop on the ground controls the smartphone in the air. Yeah, so getting to the 27th floor was a bit of a challenge. And the Mavic didn't really like the added weight, but he managed. And here on the table is the Aruba access point waiting to be owned. Okay, so once the drone or the smartphone is nearby, you can search for beacons. The Aruba access point is in beaconing mode, right? So you can find the MAC address by that. You can use the GAT tool to find the OBD service. And then we wrote a small script that just uses the hardware, the password we retrieved from the firmware, and uploads our own malicious firmware. This is a bit sped up, but it takes about a minute to upload a firmware. So that firmware allows us access unauthenticated to this shell interface. So we just use the shell access on the AP, and through this BLE connection, we can change network configurations. We use ifconfig, route, all of these commands. And you can also send packets within the network. There is the ping command for that. An interesting aspect is that the BLE is connected to this console interface even throughout a reboot of the device. So by rebooting the AP through this interface, we can access the bootloader shell over this BLE connection and change boot parameters, maybe potentially even upload like an older firmware version of the entire AP or something. Yeah, as I mentioned, if the attacker does achieve code execution on the main CPU, he can create an outbound connection, and then the vicinity of the drone is no longer needed. Okay. Yeah, so this is one vulnerability, the Aruba one. It's significant, but we have more to discuss. So this second vulnerability, as I mentioned, is in TI's BLE stack, and it affects the Cisco and Meraki access points, but potentially other devices. And this vulnerability is in the code that parses beacons, parses incoming packets. In BLE, you have different roles. A device can be scanner role or an advertiser role, and it's simple, right? One device will send out beacons through what is called advertising packets, and the other will listen to these packets and parse them as they come in. And you have 3 channels that are fixed channels for advertising packets on BLE, and so the advertiser will send these packets on all of these channels, and the scanner will hop between the frequencies and listen to these packets. A BLE packet has a structure that is pretty straightforward. You have a preamble, a fixed access address, and then a PDU that is different between if it's advertising channel or another channel. In advertising channel, you have a 2 bytes header, and then up to 37 bytes of payload. This 2 byte header is built up with different flags, but there is one interesting piece here that I want to mention. There is a length field in the header, and that actually changed. The length field changed between Bluetooth 4.2 and Bluetooth 5. Bluetooth 5 is now becoming introduced into the market, so chips are being designed to use this new protocol. And the length field between Bluetooth 4.2 and Bluetooth 5 increased from 6 bits to 8 bits. And in the older version, in 4.2, there were an additional 2 bits in that byte reserved for future use, RFU bits. And they were also always supposed to be 0 bits. So this change in the specification might have, in retrospect, led to the vulnerability that we found. We're not sure, but this looks ominous, right? The fact that the length field changes as a potential for bugs. looking specifically on the architecture of TI's BLE chip, it's quite an interesting device. You have 2 cores. You have the main CPU that's running an ARM CPU, and this one does most of the logic, most of the BLE stack logic. And then you have your radio core that also runs an ARM CPU, and that one does the more physical layer stuff and really the low-level handling of packets. And the link layer is actually split between these 2 cores, and they have a shared interface to exchange the packets that are coming in. There are also systems where you have an additional CPU, like an access point. So the application layer will be split between the BLE chip and the external CPU over some interface, either UART interface or another. Like many devices, embedded devices, right? There is no inherent security in this chip. There is no use of data execution prevention, no ASLR, and no MMU. So finding a vulnerability here still has the challenge of being able to exploit it like any other vulnerability, but the chip itself will not stop the vulnerability with inherent mitigations. Okay, looking at this function, this is the function that parses advertising packets as they are coming into the chip when it is scanning for advertising packets. And it will do some parsing of the packet and some handling of different types of packets and such. And instantly we see that there are a few problems in this function. The first thing is this handling of the length field that I talked about. As I mentioned, it's supposed to be 6 bits, but this code here takes the entire 8 bits from the header and calls it the packet length, and interrupts this as the packet length. So it doesn't mask out the RFU bits, the reserved bits. And the second problem here is the third line on that red box, where the code will decrease 6 bytes from the packet length. So there is the potential here to do an integer underflow. And the data length is actually assigned integer in this if case. And so if it is a small number, if it's -1 or -2 or something, it won't be detected as a large packet. But even if it is detected, the function that is called the hull assert handler is actually a null function that does nothing. So the code will carry on, and there is a copy loop at the end of the function. Using the packet length passed to it, it will copy the packet onto the advertising data pointer. So this looks like there are many problems here, and the next step for us is let's try and crash it. Let's send different packets and see what happens. And like I mentioned, there are the length field, which is 6 bits, but you also have the RFU bits, and all the 8 bits together are considered as the length of the packet. So we have a couple of parameters to play with. Initial step was let's send the largest packet we can in the 8 bits, but it didn't crash. So, okay, something is not as expected right now. The next step was let's try and send a very small packet, right? Maybe we can hit this integer underflow, but this also doesn't crash. Next thing we thought, maybe we can't really touch these bits, the RFU bits, so let's send the largest packet we can within 6 bits. It will also be potentially out of bounds, but this also didn't crash. Just for sanity check, we decided let's send the largest packet we can within the specification limit, the 37 bytes packet. This didn't crash. It did reach the code that we were looking at, so we are partially in the right direction. And last, let's try and turn on one of the RFU bits, but keep the packet at 37 bytes. So it is a short packet, but it may be perceived by the code as a large packet, which will result in corruption. And in fact, that did crash the device. So we understood there is another mechanism here that validates the input other than the code we were looking at. What is that mechanism? As I mentioned, the main CPU and the radio core share the link layer. They both do part of it. And when we went back to the manual, it was clear that the radio core validates packets to be between 6 and 37 bytes. But when we look at the code from the radio core, we see that it looks at the length of the packet as 6 bits, as defined in the specification. Whereas the main core looked at the entire 8 bits. So this difference leads to this vulnerability. by sending a small packet, but turning on one of the RFU bits or both of them, it would result in a memory corruption. And how we exploited this corruption and on a Cisco access point, Dor is going to talk to you now.
Okay, so I'm going to dive deep into exploiting this vulnerability. But before we start exploiting, we need a victim. So we chose this Cisco API to exploit it on because it contains the CC2640 chip. And naturally, we opened it up, hooked up a debugger, and dumped the firmware and started understanding where the data that is corrupting and what are we exactly corrupting. So looking back at the vulnerable function that Ben talked about, you can see that the advertising data variable is coming from the caller function, which is advertising packet. Advertising packet is a global variable that is statically allocated in memory, which is it's an array that contains the advertising packet that has arrived, and it's in a fixed address. As Ben mentioned, there are no ASLR, no dep here, so it will be allocated at the same address every time. And there's a lot of interesting stuff to overflow after it's in the data section. So the one that sticks out the most are these three function pointers, which are system critical function pointers that the firmware uses. So the first pointer, the iCall dispatcher, is the system call gateway. Every system call that the firmware makes, every malloc goes through there. That looks like a really good target for us to control. And the other two are the enter and exit critical section function pointer, which does exactly that. Looks good as well. They are called quite oftenly, but not as much as the dispatcher. So we're going to head for it. So going back to the vulnerable function, you can see the data that the function parses is coming from some data entry queue. So we needed to do some research and understand what is this data queue and where does this data come from. So this data queue is basically 4 entries of packets that arrives from between the radio core and the main core. It is allocated in a shared RAM memory between those cores. And it's linked together to form a cyclic list, and also they are contiguous in memory. So let's go over quickly how would a packet that is being received would look like. So the radio core and the main core starts off at the start of this list. The radio core receives a packet from there, so it needs to mark the entry as being used, goes on and fills the data, then frees the entry, so the main core can now start parsing it. While the main core is parsing it, the radio core had received another packet from there and filled it up in the next entry, so the main core can go on and parse it as well. This happens in a cyclic motion, meaning that when the radio core will hit the 4th entry, it will go back to the 1st entry, and so on and so forth. Okay, so now that we understand where the data is coming from, let's look at this scenario. A normal advertising packet had arrived, and then the vulnerable function had copied it onto the advertising packet global variable. Okay, so far so good. Another normal advertising packet had come, same here. But now a triggering packet had arrived, meaning that we have turned on 1 or 2 of the RFU bits inside those packets, but it's in the legitimate length. And now an out-of-bounds copy will be initiated inside this function, and we can see that the data that resides inside entry number 3 will be copied onto the iCall pointers that we would like to control. Okay, so this gives us a little bit of hint of where will the data that we want to control will be held. If this happens in the 2nd entry, then the 4th entry will be copied onto the iCall pointers, but what happens if we trigger from the 3rd or the 4th entry? We copy data from after the data entry queue, which we cannot hope to control, and this puts this form of exploitation at 50% success rate. So now that we understand that we would like to control data entries that are not the triggering one, we need obviously to spray this data entry queue. So I'm going to go back a little bit about how BLE does its advertising. Basically, there are 3 advertising channels or frequencies which advertising packets are sent on, and the radio core is going to hop between them looking for advertising packets. So basically, if we want for the radio core to receive our spray packet every time, we're going to need to be on all 3 channels. Also, the radio core has a packet duplication mechanism that helps it prevent seeing duplicated packets, and basically it validates that it hadn't seen this packet from the same sender, from the same MAC address. So basically, we're just going to randomize every MAC address of the packet, and then we will easily circumvent this mechanism. So now that we understand how we're going to spray, we're basically just going to spray packets that hold our desired ICAL values that we would like to put on the ICAL pointers, and then after some time, we're going to trigger the overflow and do it again and again, hoping to fall into the right place inside the scanning process. So our strategy is as follows. We'll trigger the overflow from one entry while copying onto the ICAL pointers. And now we need to put meaningful values inside those ICAL pointers so we could execute code. So as Ben mentioned, we have no dep here, meaning we can execute data. And we know exactly where our overflow packet will be held because it's in advertising packet. So let's put this address inside ICAL dispatcher. And then when the next syscall is called, we'll just jump onto our packet and execute our packet. Sounds simple enough, but we have a lot of limitations on this exploitation. First, every advertising packet holds 37 bytes maximum of data. So we control the trigger packet and we control the spray packet, but spray packet has 3 ICAL pointers values it needs to hold. So we are left with 62 shellcode bytes that we can use in our exploitation. This is not a lot of bytes to maneuver within, but let's talk about the task at hand that we're going to need to do inside those 62 bytes. We're going to prevent future overflow crashes. I'm going to talk about it in a bit. We're going to install some sort of backdoor because we want to keep communicating with the chip and controlling it. And we're going to need to restore the chip state. Because we are running from a syscall that runs a packet, the system thinks we're kind of in a weird state, and we're going to need to restore its original state so it will keep scanning as usual. And we have corrupted a lot of data on our way to the ICAL pointers. Basically, 109 bytes of corrupted data that was written by our overflow until we hit the ICAL pointers with our control values. This is more bytes that we corrupt than we can actually control in this exploitation because we have only 62 shellcode bytes, meaning that if we will bring all the data with us, we basically have a little bit more than half of the bytes that we need to restore. So we're going to need to find a solution for that. And also, we're going to need to return some error value because we don't have enough bytes to actually do the system call that is expected of us because we are running from a system call callback. And then we're going to need to patch the system call address back, the ICAL dispatcher back to its original value. So we won't be called every time a system call happened, and the system can continue as usual. So when I looked at it at first, I was like, oh man, it can't be done. Like, logically, we don't have enough bytes to do it. And I remember talking with Ben about it and saying, let's just not exploit this vulnerability, it's too much. But Ben told me, let's take it part by part. And so I will take you through part by part of our exploitation. So the first problem is preventing future overflows. What do I mean by that? Let's imagine a trigger packet had arrived in entry number 2 and we controlled with our spray in entry number 4. Now, the overflow will be triggered, our code will run, and everything is good in the world. But what happens if another triggered packet just arrived in entry number 3? So after our shellcode has gotten executed, the main code will go on to parse the third entry and then copy uncontrolled data on the ICAL pointers and basically crash the chip. If this is left unfixed, we will eventually sometime crash the chip. So this is bad, obviously. We need to find a way to fix it. So let's assume our triggered packet was from the second entry, and now we have executed code. We do this nifty little trick where we link the same entry that triggered the vulnerability to itself, effectively freezing other entries from being touched by the main core or the radio core, because now they don't even know they exist. And now when another packet will come, the radio core will fill the second entry, but the main core will have to wait until it's finished because the data entry queue is only 1 entry long. So now when the main core will parse it, everything is good, but now another trigger packet will come, no problem because we're in the same pool state that we used to, and now the copy will be called again, and we still won't crash the chip, but execute code again. Meaning that when we first succeed, we will succeed every time after doing this trick. This trick costs us about 3 ARM instructions. That's not a lot. And we are left with 56 shellcode bytes. Okay, so now the hard part. We need to restore execution of the chip to its original state. I don't have the time to go into everything, but I'm just going to talk about, after a lot of research we did, we found that these variables must be restored in order for the chip to be in its original state. So we wrote some code that does exactly that, but I haven't mentioned our overflow will corrupt some gap task related variables there that are 16 bytes long. So now after restoring everything that we need, and we have 17 bytes of shellcode left for us to do logic, we need to restore 16 bytes of data, which means that even we can do it in 0 instructions, we'll still have 1 shellcode bytes for our logic to do, which basically is a half of an ARM instruction. So our exploit just restores execution and does nothing. This is obviously bad, and we're going to need to go back to the drawing board and take a second look at this. So we did some more research and found out that basically if we stop the gap task from ever running again, we can just restore those 3 variables, put a null inside one of the gap task callbacks, which would make it stop running, and then we can just restore those 3 variables, making it not that byte expensive for us to restore those variables, and we now have 32 shellcode bytes for us to maneuver within. Still not a lot, but at least it's something. So now that we have restored the execution, we're going to need to install some form of a backdoor. Because we have only 32 bytes of shellcode left, we're going to need our backdoor to be really, really lightweight and size efficient. And also, we would like to put there somewhere it won't cost us a lot of time and instructions to install the hook for our backdoor. So our backdoor that we come up with will be this backdoor. It's only 8 bytes long, and it will sit, our shellcode will write it just above the advertising packet global variable. What it does is basically checks if the first 4 bytes of the packet that is being received is a magic value, in this case PC, but because everything is static, we can predict PC every time. And if it's the magic value, it will jump over it and just execute our packet. That's great. And we need some runtime for our backdoor. So remember, we control the ICALL pointers, so why not use the other 2? We'll use the enter critical section to execute our backdoor. It is called many times during one packet parsing, making sure our backdoor will be called every time a new packet had arrived. And we'll use the exit critical section basically because we don't have enough bytes in the enter in our backdoor to do the actual enter critical section. We'll just put a gadget that does nothing inside the exit critical section and render this mechanism useless, but still we get some execution time for our backdoor. So let's recap all of our backdoor. First, we set up some shellcode environment there, reading some variables into registers. Then we're going to stop the gap task from running. We're going to install our backdoor. This is 2 store instructions because our backdoor is only 8 bytes long. Then we're going to link the data entry that has triggered the vulnerability to itself, freezing other entries and making sure we won't crash in the next trigger. Then we're going to restore our corrupted values. As I mentioned, we need to restore only 2 variables, the time ahead and the BLE dispatch task ID. And then we're going to unhook ourselves from the Cisco gateway because we don't want to run again. And that's it, basically. We have exploited the CC2640 with only 32 bytes of shellcode that we had in our disposal. And now I'm going to pass the stage to Ben that's going to talk about the demo. Thank you.
Okay. So yeah, as you saw, it was quite challenging to achieve execution through this small bug, but eventually we did it. I'm going to show a short video on how this is exploited. So you have, again, the hacker. It controls a Raspberry Pi that is connected to an Bluetooth. That device can be used to send BLE packets, custom packets. And this attacks a Cisco access point. On the right, we can see the attacker scanning for BLE beacons. When the attack is finished, we will see the targeted device beaconing a specific message, So on the left, we can see the attack going on. We send the spray packets, we send the trigger overflow, and now once we have a backdoor, we upload our specific beacon data onto the device using that backdoor. And we tell the chip to start advertising this malicious beacon. And you can see on the right, the AP is saying it has been owned, and an indication of compromise from the BLE packets. So in that state, any device nearby that scans from BLE beacons, like my smartphone, will show that, in fact, the beacon is saying your APs belong to us. Belong to us. Okay, so yeah, we're really at the end. I just want to talk about 3 takeaways I think should be taken from this research. First, the fact that BLE chips, radio chips that are sometimes considered peripheral chips can also be vulnerable to attack, right? They have CPUs, they run code, they can be vulnerable. If they are vulnerable, this can lead to something greater. This can lead, in an access point environment, for example, to a network breach. So you can start for something very small like a BLE chip, but this can go on and then target an entire network. And third, the fact is that access points and network infrastructure devices in general are practically also unmanaged devices. The BLE chip inside the access point is not managed, right? The access point itself is just a device that serves Wi-Fi. It doesn't have an agent on it. It doesn't have too much inherent security. So in the global, like zooming out from the bits that we talked about into the general picture, obviously this is a threat landscape that should be looked at. We have a white paper that details all of what we talked about in detail on our website. And all the affected devices and vulnerabilities. Obviously, we did a security disclosure process, which I haven't talked about, but it's also detailed in this website. And I think we have like 3 minutes for questions if anybody wants to ask. Maybe we were really, really clear. That's a good sign. Right. Thank you very much.